That's maybe 4 somewhere.
I don't know, that's pretty.
All right, guys, I can see the audience is dwindling a little bit. So should we have like extra P sets? I'm noticing a correlation here.
Well, I mean, drop date is tomorrow.
I see.
So presumably people are dropping.
Let's take that offline. So we're going to cover a fun topic today. So first, just as a review, so we'll talk about SDPs in a little bit more detail. But as a review, last time we covered Max-Cut. That was our segue into semi-definite programs. And can anyone give me a brief recap of the types of things we covered last time? So what was the main takeaway from the previous lecture?
Max-Cut is UGC hard.
Well, I didn't explain what UGC was. Yep.
If we replace things that are usually indicator variables by large vectors, we can apply SDPs to them and then use them for something.
Perfect. Exactly. Right. So, my short summary of this is what we gave was we gave a 0.78 approx. And this was for Max-Cut. So Max-Cut was something which there's a trivial way to approximate it within a factor of 2, which was just choose randomly, and then each edge has a 50% chance of being cut. When we tried to do it using linear programs, using our usual formulation of start with the integer linear program, then create an LP relaxation, we got stuck that we only got trivial approximation algorithms. It was only when we moved to semi-definite programs, which are themselves a powerful new family of convex programs that we used, that we were able to actually beat that trivial approximation algorithm. And there's actually some evidence that the approximation factor that we gave last time is actually optimal, or at the very least, beating it would have some rather striking consequences and complexity. Yeah?
Is there a case where an LP gives a decent approximation, but an SDP gives a better one? Like the LP doesn't give...
Absolutely tons. So, the main point of today's lecture is actually thinking a bit more about how to round SDPs. So you could take entire courses on how to round SDPs, and some of the approaches get quite technically involved, but I thought I'd show you what I consider another gem in this area, which actually predates a lot of this, is what's called the Grothendieck inequality. And time permitting, we'll briefly touch on another application of SDPs to something called the Lovász Theta function. But that'll just be a quick digression to see where SDPs can figure in even when your goal isn't to design approximation algorithms, but to actually design some interesting new algorithms. So does anyone know anything about Grothendieck? Does the name sound familiar? Anyone tell me anything about Grothendieck?
He's a famous algebraic geometer.
Yep. Anyone else have any trivia about him? He's a very interesting fellow.
He stopped publishing for a long period of time and...
Yeah, exactly. So they tried to give him the Fields Medal. He refused. Burned his papers and went to tend sheep in the south of France. So he unfortunately passed away recently, but he's a brilliant guy. Has some amazing things that people are still discovering, things in his treatise. So today, we're going to mostly talk about this Grothendieck inequality. So what we're going to do is we're going to focus on another optimization problem that'll be, our main focus for today is to try and approximate it. So let me define what that problem is. So let's consider an optimization problem where we're looking for plus minus 1 values for these variables xi and yj. And what we want to do is we want to try and maximize their quadratic form on some matrix. So we're given some matrix and we try and maximize this corresponding sum. So this matrix actually need not be square. Now for most of today, we'll actually think about this as being an m by n matrix. So you're trying to choose m plus minus 1 variables for the xi's, and then n plus minus 1 variables for the yj's. And you want to do so in a way to try and maximize this quadratic looking sum. So just as a first question, to build up some intuition, So does this problem look computationally easy or computationally hard to you? Yep.
Computationally hard.
Computationally hard? Do you have any intuition for why that is? No? Just because it's not obviously easy? That's actually very good intuition anyways.
Quadratic program of,
Yeah, exactly. Exactly. In fact, what you can do is you can even think about something like Max-Cut as being a special case of this type of problem. So the difference is here we have two different sets of variables, but there are natural ways to try and force these variables to actually be the same by putting large values along the diagonal. But it's actually not hard to create a matrix A, which the optimal value will actually correspond to the max-cut in some graph. So I'll just assert this as a claim that it's not too hard to show that for particular choices of A, that max-cut is actually a special case. So this problem is definitely NP hard. That's obvious and also pretty intuitive, just because there's not an obvious way to try and solve these problems by casting them as an LP or SDP. But today what we're going to do is we're going to study a very powerful SDP relaxation for this problem. And this really will be different than the max-cut case. It'll be a little bit subtle. Let me work up towards that. So what I want to do is I want to study a family of relaxations for this problem. So let's try and do exactly what we did before. We started off in the previous lecture with max-cut, and then we moved to an SDP relaxation that we used to give a good approximation algorithm. Let's try and do the same thing. Let's try and replace these plus minus 1 variables with vectors, and let's try and approximate it via SDPs. So let me build up some intuition about these SDPs. Let me write it one way, and then we'll think about different ways to interpret it to get a better intuition of what's going on. One way that we can try and approximate this optimization problem is instead to look at some sort of sum over ij of not aij times xi yj, but times some set of variables zij. So remember, A is an m by n matrix, and z here is also m by n. Now we better incorporate some positive semi-definiteness constraints. And one way to do that is we can think about creating a block matrix, which itself has m plus n rows and m plus n columns. And we could enforce something like the fact that this matrix is positive semi-definite. So what I mean by this is that we can think about some matrix of variables, which we force the diagonal entries along it to all be 1. That corresponds to really doing an optimization problem over vectors, where the vectors are constrained to be what? Unit vectors. So I'll build up some intuition for what this is in a second by reformulating a different way. But then, because we have this asymmetry in the original problem, where we had xi and yj were two different sets of variables, we want to think about those as being associated with two different sets of vectors. So z really here is not necessarily a square matrix because it's designed to represent different pairs of xi, yj, so it's an m by n matrix. And we can think about this aggregate matrix as having arbitrary entries in the off diagonals here, ones along the diagonal, and then when we insert z here and here, we want the overall matrix to be positive semi-definite. So this is definitely an SDP. This is a semi-definite optimization problem. But what I want to do is I want to recast it in a slightly more convenient way. This will help you get a better intuition about why it is a relaxation and what actually are the useful properties of z that we'll end up exploiting. So what I claim in all of this is that the same thing is going on as what we used in Max-Cut, is that B is itself an m plus n by m plus n matrix. And because it has ones along the diagonal, we know, and it's positive semi-definite, we know that we can write it as the product of two matrices W times W transpose. Now the key thing in this is I can think about taking the first m rows out of W and the last n rows out of W, and we should really interpret those as being vector relaxations to our original plus minus 1 variables. So let me be more precise by what I mean by that. So what I claim is that we can think about the first n rows of whatever matrix W that we get out from factorizing this positive semi-definite matrix in this way as themselves being unit vectors u1 through um, and we can think about the remaining rows, the last n rows, again of W, as being a new set of unit vectors. Let me call them v1 through vn. So now, can anyone take this optimization problem and tell me a different way to write it in terms of what these vectors are? So how should we think about this objective function? Yep.
It's max aij utv, or well,
Yes. So let me state it this way. So what we're doing is we're looking for a set of m unit vectors, u1 through um, and a set of n unit vectors, v1 through vn. But now what we're trying to optimize is we're trying to maximize the sum of aij times the inner product between ui and vj. This is nothing more than what the entry zij was in our original relaxation, because an entry right here corresponds to the inner product between some vector ui and some vector vj. So this is another way to think about this, is that this is an equivalent way of thinking about what the semi-definite programming relaxation is.
This is also like exactly the same as how we interpreted the Gomez-Williams.
Exactly. So all I'm trying to do is build up a little bit more intuition about what's going on here. So does everyone see how these two views are actually the same thing for the semi-definite optimization problem? Yeah?
So the point of the ones along the diagonal is just to make it unit vector.
Exactly, exactly. See, what's the only thing that's slightly different here is that for this problem, the one that we're interested in, actually there's an asymmetry because we have the xi variables and the yj's. What that means is instead of thinking about just one matrix which represents all of the inner products, really our matrix is not square, it's this matrix Z, and it represents only the inner products between the corresponding UI vectors and the corresponding VJ vectors. So this is really similar to what we did last time, yeah?
To be clear, these are unit vectors of size m plus n?
Yes, exactly. That's another very good point, is why are they unit vectors of size m plus n? Because we started off with this m plus n by m plus n, positive semi-definite matrix B, that has this type of structure. And what we did was we factorized it as the product of W times W transpose. In general, you won't know anything about what this inner dimension is, except for the fact that it's at most the original outer dimension you started with. So those vectors themselves are also length m plus n in general. Maybe you'd get away with something smaller just by sheer chance that your SDP found, but in general you wouldn't. So are there any other questions about this? Does this optimization problem make sense? Right? So let me tell you Grothendieck's inequality now. And let me call this optimization problem star. So first of all, is it clear that this optimization problem is a relaxation to this one? So how could we think about any solution to this as a solution to that optimization problem? What did you do?
Oh, just choose two unit vectors that are, choose a unit vector, make that one, negative that is negative one, and that's it.
Right, or let me phrase it another way, which is, in particular, what you can do is you could set ui to be a vector which has xi in one coordinate and has zeros everywhere else. Xi is a plus minus one variable, so this overall vector ui is definitely a unit vector. And moreover, you can do the same exact thing for vj, which is you can put yj in there and put zeros everywhere else. And then from any feasible solution to this optimization problem that we care about that's NP hard, well, lo and behold, we can construct a feasible solution to this SDP, right? So it's actually the same type of intuition as what happened with Gomans-Williamson, that if we took the SDP relaxation for Gomans-Williamson and we actually forced it to be a rank 1 positive semi-definite matrix, we would have gotten back the original max-cut problem. That's the same reason that when we start off with a feasible solution there, we naturally get something that's also lives in a low-dimensional space instead of dimension m plus n. So let me actually just write out some notation and then I can state for you what Grothendieck's inequality is. So I'm going to let opt be the solution for the original thing and opt prime be the new solution to this SDP that we can then find out the optimal value for. And there's an amazing theorem of Grothendieck, which maybe the best streamlined proof of it really comes from an exposition of Krivine. So I'll cite them both for this. That opt, well, first of all, we have this trivial inequality that opt prime is at least opt. Why is that true? Just to make sure we're on the same page.
It's a relaxation.
It's a relaxation. The more interesting part is that there's actually, it's within a constant factor of optimal. So we're going to see another crazy constant factor coming up in here. Would you guys have guessed this one? No?
It's nicer than the last one.
Hmm?
It's nicer than the last one we saw.
It's nicer than the last one.
Yeah.
Well, the last one we know was at least in some sense optimal, that it was the right answer for hyperplane rounding. So this is actually called Grothendieck's constant. As in, whatever is the best constant you can get on this right-hand side is called Grothendieck's constant. There's some kind of amazing facts that we're not going to get into, that for a long time it was actually conjectured that this should be the right answer for Grothendieck's constant, that you can't actually improve upon the rounding algorithm I'm going to give you today based on SDPs. And then in a recent paper about 3 years ago, actually Braverman, Nauer, Makarichev, and Makarichev showed that you could subtract something on the order of 10 to the minus 10 from this, and it still helped. Which was actually amazing because it was very counter to people's intuition. I thought Kravine's bound was tight. And actually to this day, we don't actually know what the right value is for Grothendieck's constant, even though, further on down the line, people have actually given algorithms that in a finite amount of time would calculate Grothendieck's constant up to some finite precision. We just can't run those algorithms because they're hopelessly involved. So what I'm going to show you today is this part. We're actually going to see why this inequality is true. It'll be a really souped up version of hyperplane rounding, which I think what's so amazing is that a lot of these old proofs, this predates Gomans-Williamson, were actually a type of hyperplane rounding in disguise, but the fact that they were connected to things like SDPs was not obvious from the way that they were written. So actually hidden within a lot of the mathematics literature, particularly in functional analysis, there are SDPs going on behind the scenes. All right, so the first thing I want to do is I want to explain to you what's so different about this problem. At first blush, it sounds a lot like Max-Cut, right? We started off with an optimization problem that looks a bit like this. After all, Max-Cut is a special case. And then we work hard and we get an SDP with a constant factor approximation. So actually one of the first things I should convince you of is that you actually don't yet know a way that this holds with a constant factor, that just naively applying hyperplane rounding to try and approximate this optimization problem is actually going to fail hopelessly because there's an issue with what the hyperplane rounding analysis was. So I want to explain to you what the issue is, and then we're going to see a very clever way to deal with that. So
is it even obvious this is always positive, by the way?
This is getting into what I'm about to talk about. Is first I want to convince you that you don't already know this. So you don't even know this with any constant factor on the other part. Let me explain to you what's so subtle about this, right? So, the first question you should be asking to yourselves is, well, we know one SDP rounding algorithm, so can we just use it? Can we just use hyperplane rounding on our SDP relaxation And for example, can we take the optimal solution to the SDP and just set xi to be the sign of A transpose ui and yj to be the sign of A transpose vj, where A is again a uniformly random vector chosen from the sphere. So this is exactly what hyperplane rounding was that gave us our 0.878 approximation for max cut. And I claim that something goes wrong if we try and do that. Does anyone have any intuition for what could go wrong? This is a bit subtle and I'll explain it, but it's very important to understand this. Yep.
Hyperplane rounding worked well because we had exactly the same kind of constraint in the maximization problem for every point, which was that they were all getting pushed away from each other. Whereas this can have arbitrary sorts of...
Yep, that's definitely very much on the right track. Does anyone else want to add a little bit to that answer too? So what would go wrong in the types of analysis we talked about last time? I'll explain it in more detail, but I'm curious if you have any intuition. So, see, one issue is the way that our analysis worked last time was we looked at every different edge. We looked at how much their contribution was to the SDP versus what their contribution was to the expected value that we get when we do this hyperplane rounding. Now, the big issue is that that's actually a nonlinear relationship. So when we had, what we did was we said that one always gives an upper bound on the other. But the big issue is that because it's a nonlinear relationship, we actually could have that all the positive terms contribute just a little bit, and all the negative terms contribute very, very large amounts. So let me explain what I mean by that, which is, let's consider each term's contribution. This is how we analyzed Gomez-Williamson. Let's consider the contribution to both the SDP and to the expected value. So to the SDP, we know that their expected contribution, or that their actual contribution to the objective value is just Aij times the inner product between ui and vj. That's because it literally shows up in our optimization, in our objective function. But what about to the expected value if we were to do hyperplane rounding? See, what I claim is we certainly get an Aij, but now we're going to get some contribution which depends on, let me call this guy right here as before the cosine of theta ij. Well, we're going to have some contribution which corresponds to the probability that xi is not equal to yj when we actually do this out. So that's what we studied last time, was that if the angle between xi and ui and vj was theta, then actually the chance that they end up on different sides of the hyperplane was exactly theta over pi. And in that case, we would get that the product of their signs, you know, xi times yj would actually be -1 because they're on different sides. But we also have a contribution that comes from the chance that they're on the same side, right? Which is just 1 minus that probability. So this right here is just the probability that xi equals yj, and we get a +1 contribution when we take the product of those two values. So does everyone agree with this being the expected contribution to the value if we were to apply hyperplane rounding? Does that make sense? Any questions? So what I claim is we can actually rewrite this now. So I claim that we can write this out now as Aij. Let me pull out a 2 over pi in here. And this becomes nothing more than pi over 2 minus theta ij. So now if we draw a picture, a lot of it becomes clearer. So we think about some unit vector ui, and we think about some unit vector vj. And when we drop a perpendicular line down to ui, then what we're getting right here, this is the angle theta ij. This quantity right here, what is it? in terms of theta ij? Yep.
Bj cosine theta ij.
Yeah, these are all unit vectors, so cosine theta ij. Good. So what I claim is that this pi over 2 minus theta ij is exactly the angle right here. So in fact, what we get out from this term is nothing more than the arc sine of the inner product between ui and vj, right? So this is the big issue, is that we have some term right here, which the way that it contributes is some constants, not a big deal, times some extremely nonlinear function of what its contribution is to the SDP. So to make this more precise, what we're really worried about is the following. Right? So what if the SDP, we look at all of the different values in the objective function. What if there's something that contributes +7, something that contributes -6, something that gets +7, something that gets -6, and so on? Well, the real problem is that the value that we would get from rounding, all of the positive terms might actually only get some alpha times their value, and all of the negative terms might get their full value. Applying hyperplane rounding might give you something which is arbitrarily close to 0, because all the terms which contribute positive contribute at most an alpha. All the terms that are negative might contribute their whole value and actually cancel out that positive part. So does everyone understand why this is a big issue? Yep.
Can you explain why the minus terms don't have an alpha?
So alpha was a statement about when we talked about hyperplane rounding. For every possible edge, forget this aij, what it said is that we can actually show that the contribution to the expected value is at least some alpha times its contribution to the SDP. That doesn't mean it's always equal to alpha times the value. It could be something more than alpha times the value. So what if all of the things that we want to go one direction only contribute at this rate alpha, which underlie the Gomans-Williamson rounding algorithm? And what if all of the negatives contribute at their worst possible rate? This could mean that we actually get much more cancellation and we get something that's very close to 0 for expected value. Yeah.
So essentially the claim is that the contribution to the value is like bounded by some constant times the contribution to the SDP, which was fine in the case of Max-Cut because it was always the same sign, whereas in this case it doesn't work.
Perfect. Does everyone understand that? So this is a very subtle point, but we're going to resolve this issue in a kind of clever way. So hyperplane rounding is not the end of the story. So the first thing I want to do is I just want to collect this fact that we established right here, and then I'm going to tell you how Grothendieck and Quadratic deal with this problem. So this is the basic fact from hyperplane rounding. This is the real upshot from the Max-Cut lecture, is that if we look at the expected value of the sine of A transpose Ui times the sine of A transpose Vj, then what we get is exactly 2 over pi times the arc sine of the angle of the inner product between Ui and Vj. Okay? So this is the basic fact that was underneath our alpha approximation algorithm for Max-Cut. And this is the basic issue that we have to try and circumvent, the fact that the expected value that we contribute to the actual rounding of the solution is actually an extremely nonlinear function of what its contribution is to the SDP itself. So let me tell you an amazing idea. So I can't believe this thing works, and I have very little intuition for it, but it does work. So here's the main lemma behind this Grothendieck inequality. let's create new vectors. So here's the main lemma from which everything else will follow. And this lemma itself is not that hard itself. It turns out that for any unit vectors, let's say u1 through un, v1 through vn, to be consistent with our notation, there's actually a completely new set of unit vectors. These are again unit vectors. Let's call them u1 prime through um prime, v1 prime through vn prime, with the property that rounding them gets us exactly what we're looking for. That if you look at the expected value of sine of A transpose u I prime, sine A transpose Vj prime, this is actually exactly equal to 2 over pi, natural log of 1 plus root 2, times the inner product between ui and vj. So you can actually undo the arc sine. Isn't that weird?
But oh wow.
Doesn't sound true, right? In
Maybe
fact,
it
we're
makes
gonna.
more sense to think about this in the SDP matrix world than it does in the actual sense of vectors here. I mean, it's still surprising, but
It's very surprising.
Wait,
It's very surprising. So does everyone understand why this is surprising? That's the first step, because you should be surprised.
I mean, so this is really saying that if you
Vectors.
take the matrix, the
Uh-huh.
PSD matrix, and that there's a way of changing the entries that like inverts that function of the entries, or some function.
Yeah,
of
I
the
mean,
entry,
you're
okay.
essentially inverting this arc sine.
And it will keep it PSD.
Yep.
So it's basically the statement that if you have a matrix which runs the diagonal,
Not the PSD. We'll get into that.
not right.
What is the problem in the nonlinearity again
Uh-huh.
in the arc sign? Like,
Oh, okay. See, the thing is that what we said, so if we take for granted this fact, which, you know, its proof is really here, and it's just the reformulation of what we did for Gomez-Williamson. So the issue is that term by term, if we ignore the AIJs and just think about each term, well, you know, we have some contribution of the SDP, but the contribution to the expected value that we get from randomized rounding is something that's very nonlinear as a function of what the value was in the SDP. So the issue is that alpha, the Gomez-Williamson thing, tells us that we can always lower bound what the contribution is to the value based on the SDP. But now the big issue is that that's not a linear relationship. So all the things that we want to be good might only contribute at the alpha rate. All the things that prevent us from getting a large value might contribute at their max rate. So just as a hypothetical experiment, imagine I had some relaxation, which its actual objective function was summing up a bunch of things, and it was +7, -6, +7, -6, and so on. The issue is all of the +7s might only contribute +7 times alpha. All the -6s might contribute -6. So all of a sudden, you could actually, you know, for some values of alpha, you could get 0 there on the right-hand side, even though the value for your SDP was something strictly positive.
so I thought the problem was that you had some possible negative contributions, but let's say all the contributions are non-negative,
Yep.
and you had some nonlinearity.
If all the contributions are non-negative, it's not an issue.
Okay, so both of them combine
Yes,
the cost.
exactly. The issue is that you could have wildly different cancellations because of this nonlinear relationship.
Okay.
So we're going to prove this lemma. This is from which everything else follows immediately. But you know, one of the catches is the u primes and v primes are actually going to be infinite dimensional. So why not, right? So we'll deal with that later. Why exactly we do that will become clear. So the first thing I want to do is I want to show you that actually if we have this lemma, that it would actually imply this theorem of Grothendieck and refinement. So let's see why that is. It's quite intuitive, but let's make it actually precise. So let's prove the main theorem. In fact, the way that we're going to do it is let's consider what I'll call a Grothendieck hyperplane rounded. So can anyone guess with this lemma in hand, how should we do hyperplane rounding? How does this lemma suggest a fix? Yep.
So instead of rounding the UI Vj, you round the UI prime Vi.
Perfect. That's exactly what this lemma is suggesting. The lemma is really the statement that that works. So what we do in this Grothendieck rounding is, well, we find these unit vectors from our optimal solution to the SDP, which let's call them UI Vj, just as we did before. And this has the property that the inner product between UI and Vj is actually equal to Zij. Well, that's a very natural step. The next thing we do is we find these unit vectors. Actually, the proof that I'm going to give is going to create unit vectors that are infinite dimensional, but there's a way to fix that to get them to be finite dimensional, so let's not worry about that for the time being. But you're going to create these new vectors that the lemma suggests, that it tells you they're out there, as in this lemma. And all you're going to do is you're now going to round those new vectors. So again, we choose A uniformly at random from a sphere, and we set xi equal to the sign, not of A transpose ui, but A transpose ui prime. And correspondingly, yj is going to be the sign, not of A transpose vj, but vj prime. So that's it. And in fact, the analysis is completely straightforward from the lemma. All we do is we consider some term, and we look at its contribution to the SDP, which in this case is Aij times the inner product between the two vectors. And what that gives us in terms of our expected value is exactly this quantity right here, is 2 over pi times the natural log of this 1 plus root 2 times Aij times the inner product between ui and vj, because what we actually pull out from the expected contribution to the actual solution we find, Aij times the expectation of xi times yj, which is exactly what this lemma gives us. So that immediately implies the approximation ratio that's in Grothendieck's inequality, as it comes directly from this main lemma. So all I'm trying to do is convince you that this main lemma really is the heart of the issue, that it fixes this issue that we had a nonlinear relationship between the SDP value and the value that we get from our rounding algorithm, because this lemma allows us to essentially invert arc sign. Yep?
When we sample A from the sphere is infinite dimensional, right?
Right, so it turns out, and I am not going to get into this issue, the things I will do to construct, to show this lemma, will be infinite dimensional, because they're going to come from a Taylor series. But it turns out that, since there are only m and n different vectors you care about, you can always reduce to an m plus n dimensional subspace, preserving all of the pairwise inner products, and then you choose the A from that dimensional representation. But let's not worry about this technicality. That is definitely an issue with implementing it, but I'll assert that there is a way to fix it. Are there any other questions about this? Make sense? Yeah?
Is that ratio better or worse than alpha?
Oh, it's worse. So this is a 0.56 approximation algorithm. So it's a bit better than a half, but way worse than things like Gomans-Williamson.
I guess it couldn't be better than alpha.
It could not be. In fact, even for problems in between this and Gomans-Williamson, there's still, I won't get into that, but there are other problems in between that have strict constants which are in between as well. All right, good. So let's prove the main lemma. So this is going to be crazy. That's why I wanted to do it. Let's actually not that hard, so I think I can do it all over here. So what I'm going to do to prove this lemma is, well, I'm going to guess a constant. But you should really think about this guess is going to look a little strange, but you could have just done the proof and then figured out what this constant needs to be after the fact. So let me guess a strange constant, just for the heck of it. Let's say C is the inverse hyperbolic sine of 1. So this looks really, really strange. This is where the natural log of 1 plus root 2 is. You should not think of this proof as just, wow, you must have needed to know what this constant should be in order to make it work. Really, you'll see what the intuition is, that you're just playing with a constant and then figuring out how to set it to make the things that we do for these ui primes become unit vectors. So that's exactly where it comes out. So don't worry about this for the time being. But what I claim, this is the main heart of this, I claim by Taylor's theorem. So we're actually going to use Taylor's theorem now, not for analyzing things like gradient descent and interior point values. We're going to use it to design rounding algorithms for SDPs. Well, if I take our familiar sine function, and I take the sine of C times the inner product between u and v, then we can write out what the familiar Taylor series is for this. So all it is we get alternating terms, which, we have some constant in here that goes up to the c to the 2k plus 1 over this factorial times the inner product between u and v to the 2k plus 1. So you can check that, if I plugged in a value x for c times this scalar, u transpose v, that you would get out the familiar Taylor series. And all I'm doing is I'm plugging in for x and getting out this corresponding value.
Did you want -1 to the?
Oh, sorry, yes, -1 to the k, thank you. That's a big, important aspect of this. So here's the main idea behind this is, from this Taylor series, we're going to pull out what the infinite dimensional vectors are, these ui primes and these vj primes are, just by inspecting. So let me introduce one piece of terminology, which is important for thinking about what the vectors should be. If I think about some vector u, I can introduce this notation, u tensor 2, which all it's going to do is it's going to take the first coordinate of u and square it. And then its next coordinate will be u1 times u2. And its next coordinate will be u1 times u3, and so on. So if it were a length n vector, I would get out a length n squared vector in the obvious way by looking at a much longer vector, which is all the pairs of the coordinates. See, what I claim is that this inner product between u and v raised to the 2k plus 1 power can actually be expressed as the inner product between a high tensor power of u and a high tensor power of v. What should the powers be here? 2k plus 1, right? Simple question. 2k plus 1, right? One way to think about this, if you take something like uv inner product squared, that's actually the same thing as taking u tensor 2 and taking its inner product with v tensor 2. So that's something that you can check and is very straightforward. But now we're actually in great shape because we can look at this expression for the Taylor series and actually guess what the u prime should be. So u prime, what it's actually going to be equal to is, let's guess the following vector. So I'm going to take whatever this constant c is, and I'm going to create a term which depends on just the k equals 0 case of this Taylor expansion. Then I'm going to plug in the k equals 1 case. So I get a minus 1 in here times square root of c cubed over 3 factorial times what type of vector? U what? Tensor 3, exactly. And this keeps going, so that what I'm doing is I'm just concatenating longer and longer vectors exactly given by what this Taylor series is. So I get a U tensor to the 2k plus 1, and so on. Now what I claim, just to make sure that we're not losing track of the goals, so this is how I constructed U prime, right? So what's left is to construct V prime and then figure out how to analyze it. So the first thing I want is I want that, well, I guess let me just tell you what we're going to choose for this. So let me tell you what's going to work for V prime. We're going to actually do the same thing, except the only difference is we're not going to have any negative signs at all in any of these vectors. Anyone have any intuition for why I'm removing the negative signs from V prime? Yeah.
If you still have the minus signs, then when you took the inner product, the negative signs would go away and you get some all positive terms.
Perfect. Exactly, right? Because with this choice of U prime and V prime, what am I really saying is that then the inner product between U prime and V prime is equal to what? This is a very clever proof. We're actually almost done with it. What's it equal to?
The original.
It's equal to sine of C to the power of C.
Exactly. I'm just asking these obvious questions just to make sure that no one's getting lost. So this is all we did was we somehow took the Taylor series and pulled out of that Taylor series infinite dimensional vectors whose inner product gives us something that's nice. See, what's nice about this is that when we take the arc sine out front, that's actually going to go away and we're going to get something that's linear as a function of the original U and V. When we take arc sine of U prime V prime, which is what we get. Is there a question?
So wait, we haven't used C yet.
Nope. Let's use it now.
Okay.
I claimed that C is kind of a noise thing that you would just choose at the end once you came up with this very clever proof. So by construction, we have this property. And what I claim, to really finish this thing, is that, well, we care about what the 2 norm is of U prime, right? So if we actually took U prime and took its inner product with itself, then what's going to happen is we're exactly going to remove these minus signs, and the same thing happens here. So actually you can just check that what happens if I take that expression on the right, the Taylor expansion for sine, and removed the minus signs as you would get hyperbolic sign. So that's exactly where the hyperbolic sign comes in, is that you can check that you exactly get out the Taylor expansion for hyperbolic sine of C times, well, the original thing. Now, the unit norm of U is unit norm, so we exactly get sine H of, now let's plug in what C was. And lo and behold, the reason we chose that value for C was just so that we got unit vectors at the end of the day. So now, in fact, this is true even for V prime as well. So same exact thing happens because we're taking the same expression without the minus ones in there. And lo and behold, we also have that V prime as a unit vector. So at the end of the day, just to finish all of this, let's put it all together. We have our unit vectors. We know from the fact that the expected value of the sine of A transpose U prime times the sine of A transpose V prime is itself equal to 2 over pi arc sine of inner product between U prime and V prime And lo and behold, we're in great shape now because we get this 2 over pi. And then what do we have? Well, we can take the arcsine of both of these things, and we get arcsine of u prime v prime is actually equal to c times uv, the inner product between them. And that's the proof.
Wait, this is actually super general. Like you could do this with
Oh,
lots
yeah.
of functions other than sine and still have. the
Yeah,
same
yeah, that's
work.
why I wanted to show this one. So this one, for some reason, doesn't get covered in typical classes. Actually, I think no one teaches this at MIT. So you guys can now, use your knowledge for evil on your classmates. I don't know what you want to do with this, but it's a really cool proof. Because it shows you, I think, a little bit some of the capabilities of SDPs that, the first time when you see hyperplane rounding, you think of it as a great trick for dealing with Max-Cut. But what's nice is that you can even take SDPs and play with what the actual vectors are. You can do hyperplane rounding to other proxy vectors that give you interesting things. And there's an entire course that you could do beyond this. There are things like, approximation algorithms for things like sparsest cut that we haven't talked about that are very fancy. So this is just meant as a kind of general introduction to SDP rounding. This is actually probably the last SDP rounding algorithm we're going to do. But if you guys have any questions, ask me about this. Otherwise, I'm going to move on to another application of SDPs, and that'll be the end of the SDP units, is to the Lovász Theta function. Yeah?
So for the actual algorithm, are we actually dealing with these infinite unit vectors, or are we just using them for a proof?
We're just using them for the proof. There actually is a way to run this proof through without actually creating infinite dimensional vectors. See, once we know these infinite dimensional vectors are out there, we can actually, it already is implied that there is a much lower dimensional set of vectors that also has the same pairwise inner products, because we could just restrict to their span. So there's a way to do that actually in the rounding algorithm, so that things like, choosing A is then well defined because we are only in m plus n dimensions.
So another way to look at it is we know what the inner products between all of the vectors are. So the u prime v prime, or sorry, I got a u and a v inner product. U prime v prime, we know automatically by definition with this sign. This is what we're trying to get.
Exactly.
But if we also wanted a u and a u or a v and a v, the same argument would show that you just get the cinch instead of the sign. So if you can write down all the inner products, then you could just write down the inner products in like the SDP form in the first place, and then factorize that matrix.
So yeah, so there's a subtlety though. Let's take that offline because there's a subtlety to the
They have to
asymmetry.
use the signs and the cinches, not all signs.
Yes, exactly. There's a subtlety to the asymmetry in this, how u prime is actually defined differently than v prime. So actually the optimization problems you get where you don't have xi and yj, but you force them to be equal actually is a genuinely much harder optimization problem to solve. That's hard to get right within even logarithmic factors. Yep.
So in the case of original hyperplane rounding, you can think of it as you just choose a hyperplane, everything on one side is 1, everything on the other side is -1.
Yep.
What does the hyperplane look like in the original dimension?
Well, I
Is
mean,
there
what you could do, but I don't recommend you do this, is you can back out from how you're taking a vector and mapping it into high dimensions, and think about you're choosing a random hyperplane in that dimensional space.
Right.
That really corresponds to a sort of skewed way of choosing the hyperplanes in the original space. But that's very complicated, so let's take that a little bit offline. But
Also, if you're a machine learning person, what you could say is we just defined a kernel.
yeah,
There really is a
let's-
it actually really
let's
is.
not get into that.
This really is the kernel trick in some sense.
Okay, cool.
All right, everyone like this proof? This is one of my favorite ones. And this is extremely old, actually. So this is probably 40 years old or something like this. It's amazing what was done in some of Grothendieck's work. All right, so what I want to do briefly is, it's a shame to at least, talk about SDPs and not talk a little bit about some of their applications beyond just approximation algorithms. Really what was going on here was that people in functional analysis cared about just these inequalities of how well opt and opt prime approximate each other. And it just so happened that their arguments for actually proving those inequalities were based on some notion of efficient reasoning based on SDPs. So this happens a lot, that a lot of times SDPs are your basis for your proof technique. So there are a lot of areas within combinatorics and graph theory where that's exactly the case. I want to give you one more taste of that before we move on to even more experimental topics next time. But let me tell you about the Lovász Theta function. So this is another one of my favorite topics. So the Lovász Theta function, let me introduce a little bit of terminology first. So let's go back to graph theoretic problems for the moment. And let me just introduce a little bit of notation. So I'm going to let alpha of g, where g is some undirected graph, be the size of the largest independent set. Okay? And I'm going to introduce one other parameter. You could do a ton of parameters, and the Lovász Theta function, which is based on STPs, would tell you something very interesting about all of them. But let me focus on one particular pair, which is the size of the largest independent set and the chromatic number, so the minimum number of colors you need, not the color G, but the color G prime. Here, G prime is the complement of G, where every edge becomes a non-edge, and every non-edge becomes an edge, right? So that's why I'm using chi bar of G, because it's actually chi of G bar, really. So what I claim is that there's actually a simple relation between these two. So can anyone relate these two parameters, alpha of G and chi bar of G? Yep.
Chi bar of G is going to be at least alpha of G.
Yes, exactly. So what I claim is just that alpha of G is itself the lower bound on chi bar of G. One way of thinking about this is that if I had a large independent set in the graph, then when I take the complement, that becomes a large clique. And that large clique needs at least its number of vertices, colors, in order to have a proper coloring method. Now, what the Lovász Theta function is instead we consider the following optimization problem, which is an SDP relaxation for the independent set. So we're going to look for the smallest value of k with the property that there are vectors v1 through vn with the property that the inner product between vi and vj is equal to -1 over k minus 1 for all things that are not edges. So for every pair which is not an edge, we want that these vi and vj actually have a pretty large angle, larger than even 90 degrees between them. And moreover, we want that these guys are all unit vectors. So the goal is to try and minimize the value of k so that this is true. So does everyone agree that this is a semi-definite program? So this is, as you get more and more familiar with SDPs, the first way that I took this optimization problem we studied in the beginning and wrote it as an SDP was by writing out explicitly the matrix which we have a positive semi-definiteness constraint over. It was this thing with ones along the diagonal and then z transpose and z up and down. But eventually, when you get used to SDPs, you should really just think about them as being optimizations over vectors. The catch is that you can never look inside the vectors. You can only care about what their inner products are. So the same way this is an optimization problem with linear constraints on the different pairs of inner products, because we have that these are unit vectors and that these are at high angle. So this smallest value of k is actually called theta of g. So this is called the Lovász Theta function. Where else have we seen Lovász's name in this class?
Extension.
Lovász extension, right? All right, so the Lovász Theta function, a completely different object. And the main theorem is actually that this theta function sits in between alpha of g and chi bar of g. That's what we're going to prove. It's a very easy proof.
Even though both of those are NP hard individually.
Yes, even though both of those are NP hard, there's a parameter that sits in between them that you actually can compute. So this is very powerful. Let me actually just prove this theorem for you because it's a very, very short theorem. But then I'll tell you about why exactly it's so powerful and what it implies. Okay, so one direction is just that we want to prove that this inequality holds. Now, what we want to do is we want to construct a good solution to the SDP. So what I claim is, and this is just a basic geometric fact, and it's easy to actually construct vectors that have these properties. There are actually k unit vectors, u1 through uk, where the inner product between them is actually equal to -1 over k minus 1. So the way to think about this is let's plug in k is 2. So I want to create two unit vectors with as small as possible an inner product, so they're as far away from each other. So what does the trick? Just antipodal pairs, right? And then lo and behold, k is 2, I would get -1 for that, and that's exactly what their inner product would be. But in general, what you can do is you can take the simplex, and let me draw it in 3 dimensions now. Let me explain where these vectors come from. Is you can take the simplex, and you can take the center point for the simplex, and then the vectors that you're going to choose are going to be the vector that takes you to the different corners. And you can just plug in the values for what you should get and actually check that those unit vectors, if you scale them up to being unit vectors, would actually have the pairwise inner products there. I'm going to leave that as just an exercise because it's a really boring calculation. But the point is that this implies one direction. So now what we know is that any k coloring of G bar, well, I claim it actually yields a feasible solution. What feasible solution is that? Yep.
Choose the corresponding one of those unit vectors for each color.
Exactly, right? Because then, when I take any pair of vectors which are not connected by an edge in G, that means they are connected by an edge in G bar, which means that they must have different colors. So they must correspond to different ones of these vectors and actually have inner product -1 over k minus 1. So that's one part of the proof. The other part of the proof is actually equally easy. So what I claim for the other side, let's prove the other side of this. Let's prove that alpha of G is itself upper bounded by theta of G. So the way that we can do this is, what I claim is, we can take some optimal solution to the SDP, and we can take vectors v1 through vs of an independent set. Now, what I claim is, we can just take a vector, which itself is the sum of these different vectors inside this independent set, and take its inner product with itself. This quantity is certainly non-negative because it's a vector. So its inner product with itself is non-negative. Now the important thing is that when I actually create the cross terms here, I'm going to get S for all of the VI inner product VI. But I'm going to get a bunch of these cross terms, which are sum over all I not equal to j of the inner product between VI and Bj. So what this implies now is if I pull the s over to the other side and have a minus s, well, how many terms are there here? There's s choose 2, right? So there are s choose 2 terms. And what this means is then, by averaging, I claim there exists a pair, I not equal to j, where this inner product between vi and vj is at least minus s over s choose 2, which is nothing more than minus 1 oops, sorry, there are 2 times s choose 2 terms, and I get nothing more than minus 1 over s minus 1, right? So now I'm actually in great shape, because what I claim is that now this inner product between vi and vj is actually minus 1 over theta of g minus 1. That's just by the definition of optimality. This, lo and behold, we know is at least minus 1 over s minus 1, and rearranging finishes the proof. So this is actually quite amazing. I mean, it doesn't look as amazing as it is right now. But let me tell you what some of the implications are of this. So let's actually just have a slight philosophical digression about where this result actually fits in, which I think is quite neat.
Sorry?
Are there any questions about it? So now we enter the more fuzzy part of the discussion. So what I claim is that there are important graphs where alpha of g is actually equal to I bar of g. One special case, I mean, there are richer families than that, are what are called perfect graphs. So perfect graphs is a huge area of study within combinatorics and graph theory. What this simple SDP tells you in this proof immediately implies is that for perfect graphs, you can compute the largest independent set size, right? Because we know that we can compute theta of g, which is itself sandwiched in between 2 things that, lo and behold, are equal. So the amazing thing is that from this SDP, you can not only compute alpha of g, but you can actually, if you work a little bit harder, not too hard, you can actually figure out what the largest independent set is. So amazingly, even though there's a very simple SDP algorithm for doing that, the simplest combinatorial proofs we know that don't go through SDPs are actually hundreds of pages long for getting these same types of algorithms without going through this language. So it's not even clear whether there should be a simple combinatorial proof of some of these types of facts, but lo and behold, we get a powerful algorithm. One of the other ones, which I'll just mention as a quick digression for those of you who know this. So, about 20 years ago, there was actually a huge amount of excitement about a result out of Russia that seemed like it should be on the way towards proving p not equal to np. So it was a result of Razborov, which what he showed was he showed for certain types of circuits, monotone circuits, he showed lower bounds that actually there aren't polynomial size monotone circuits for computing alpha of g. So this caused a huge amount of excitement because even people in this department were eagerly waiting for the fresh manuscript to be sent across the Atlantic. And one of the amazing things was that people realized that actually those proofs, they work not only for alpha of g, they also work for chi bar of g. And in fact, they don't actually use any properties except for the fact that it's sandwiched in between. So for any parameter in between alpha of g and chi bar of g, they actually implied circuit lower bounds that were super polynomial for some restricted family of circuits. But Ava Tardosh noticed this and realized that they actually apply to things which we actually can compute in polynomial time, like the Lovász Theta function. So this was one of the other great surprises, was that actually you can compute things with SDPs that even these powerful families of circuits that people 20, 30 years ago got really excited about lower bounds for cannot compute. So I'll end there. That's a little bit of a digression, but just to tell you what we're going to do in the remaining lectures is I want to give you a sort of broader taste of algorithms beyond some of these classic topics like SDPs. So we're going to do things like compressed sensing, random matrix theory, and some other a little bit more experimental topics. So you guys will have to bear with me as we do some fun stuff. All right.